Sampling distributions. When a population grows too large to collect data from 100% of it, sample data can help us draw conclusions about the larger scale. In sampling, two terms are important to understand. First term is the parameter. It is the number that describes some characteristics of a population. For example, the mean income of a neighborhood could be a parameter. Statistic is another term. It's a number that describes some characteristic of the sample. For example, the salary of one employee in a company census. Let's say we are finding the average salary among households in one state. How can a random sample produce an accurate mean? Well, different samples of households across different neighborhoods would have to produce different averages, right? Well, this is true, but the world of statistics already accounts for this small fact. This is called sampling variability. It means that the value of a statistic can change in repeated random sampling. The sampling distribution is the ideal pattern that would appear if all possible samples from a population were taken. Consider the following scenario. There are 100 colored marbles in a bag, and the parameter is the proportion of blue marbles. You choose a sample size of 5 marbles. After finding the proportion of blue marbles in the sample, return it to the bag and repeat the process. Continue this until all possible combinations of samples have been selected and the sample proportion, or lowercase p with a hat on top, is calculated for each, then graphed. This is a sampling distribution. That sounds impractical, right? Well, you are correct. It would be very difficult to find all the possible combinations of 5 marbles from the population of 100. In statistics, simulations that run many samples are used to create an estimate of the sampling distribution. Going back to our marble example, given that the parameter is the actual proportion of blue in the population, lowercase p with a hat on top is equal to 5/10, a simulation creates the dot plot below after it generates many samples and calculates the sample proportion of blue marbles. If we calculated the mean of all these sample proportions, we would get a value close to 5/10 or 1/2. In fact, if we found every possible sample, calculated the proportion of blue marbles, then found the mean of those sample proportions, we would get exactly 1/2 or 5/10. This is called an unbiased estimator. A statistic is an unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter being estimated. Recall from earlier that the mean and standard deviation of a random variable x are mu with x in subscript, meaning the mean of the random variable x is equal to n times p, and sigma with capital X in subscript, or the standard deviation of it, is equal to the square root of n times p times 1 minus p, all underneath of the radical. Also recall that the sample proportion, or p with the hat, is equal to the ideal in sample divided by the size of the sample, or the random variable x divided by n, which is equal to 1 over n times the random variable x. Using substitution for what we have for the sample proportion, the formulas now become the following. For the mean, we'll have mu with p hat in subscript is equal to 1 over n times p, which simplifies to just p. And the standard deviation, or sigma, with p hat in subscript is equal to 1 over n times the square root of n times p times 1 minus p in parentheses, and with the remaining 3 terms being below the radical. Well, that does simplify to this quotient inside of the radical, and here's how. Well, we know that 1 over n is equal to the square root of 1 divided by n squared. and we're multiplying it by the square root of np times 1 minus p, and this is over 1, and the radical can be brought down to the whole thing because the square root of 1 is 1. And then if we multiply these together, we end up getting n times p times 1 minus p in the numerator and n squared in the denominator, and all of this is inside of the radical still. And this n cancels out with one of the n's in the denominator, leaving us with the square root of p times 1 minus p all divided by n as the standard deviation. To summarize, given a sample size n from a larger population, capital N, with a proportion p of desired outcomes, let p hat be the sample proportion of desired outcomes. Then, 1, the mean of the sampling distribution of p hat, or the sample proportion, is mu with p hat in subscripts, which is equal to p. And the standard deviation of sampling distribution of our sample proportion p hat is equal to lowercase sigma with p hat in subscripts, which is equal to the square root of p times 1 minus p all divided by n, as long as the 10% condition is satisfied, meaning that lowercase n is less than or equal to 1 divided by 10 times the larger population, capital N. As the sample size increases, the sampling distribution of our sample proportion p hat becomes approximately normal. The sampling distribution of p hat will have an approximately normal distribution provided the sample size is large enough. To determine if this is true, we use the large counts condition, which requires both np and n times 1 minus p to be greater than or equal to 10.